Today we're going to look at experimental rate laws. That is, how to determine a rate law from experimental data gained in the lab. The rate equation that we're looking to develop has the general form R rate equals the rate constant K times the concentration of A, which is a reactant, raised to some power X, times the concentration of reactant B raised to some power Y. The number of reactants you have in the rate equation depends on how many reactants there actually are in a given equation. This one particular general form reflects the presence of two reactants. In general, as noted, we want to determine the rate law from experimental data. And we can imagine that we have the reaction of nitric oxide with hydrogen to produce nitrogen and water. What can we use the experimental data to determine? In this instance, we're going to focus on three things: the rate law, the rate constant, and what the rate will be with a given set of reactant concentrations. Here is the kind of data that you can expect to see in a problem like this. Three different experiments where concentrations are varied each time. There's a key factor here. If you look at a comparison between experiments 1 and 2, you'll notice that the concentration of H2 remains constant while the concentration of NO is doubled. This allows us to explore the effect of changing the concentration of NO on the overall rate. Clearly, if we're leaving H2 the same, it's not going to impact the rate, but NO may. The other thing you might notice right off the bat is that if we double the concentration of NO, we're basically going from 5 to 10. We will quadruple the rate. 5 divided by 1.3 is approximately 4. So doubling the concentration quadruples the rate. We can express this exponentially. We can say 2, the doubling, raised to the second power equals 4, the quadrupling. That's how we know this is second order with respect to NO. We could set this up in a more formal way. We already know the rate law has the form rate equals K times the concentration of our reactants raised to some power, here X and Y. So if we plug in all the numbers from rate 2 here, we can rinse and repeat and plug in all the numbers from rate 1 in the denominator. A couple things will happen here. We can see that K is going to cancel out immediately, as well as the concentration of the reactant H2 that we are holding constant. So we see once again that the rate is quadrupling while the concentration is only being doubled. Therefore, as previously noted, 2, the doubling of the concentration of the reactant raised to some power is going to equal the quadrupling of the rate. X must be equal to 2. So, we have completed the first step of developing our rate law. We know it's second order in NO. We need to continue to find out what the order of the reaction is with respect to H2. Now we're going to look for experiments where NO is held constant, but H2 is changed. Once again, here H2 is doubled. So this will we will now need to analyze experiments 3 and 2. We notice that when the concentration is doubled, the rate is doubled. So H2 is having an effect on the rate of the reaction, but not as powerful an effect as NO. Doubling the concentration leads to a doubling of the rate. We can do exactly the same setup as we did the last time, except in this instance, we're going to be taking rate 3 over rate 2. And once again, plugging in all the numbers, seeing that the rate doubles in concert with the concentration of H2 being doubled. This allows us to figure out that we are first order with respect to H2. 2 raised to the first power equals 2. So our y exponent equals 1, and we now have a preliminary rate law. Rate equals k times NO raised to the second power times H2. Why preliminary? Well, we have the rate constant that we now need to calculate. The rate constant can be calculated by using the data from any one of these experiments down here. It really doesn't matter which one. Randomly, we're going to select the data from experiment 2, and we're going to plug it into a rearranged equation, which you see here, in order to figure out the value of k. And we're going to be very careful about our units, because that's something you frequently encounter as a question. If you just identify k numerically and you get the wrong units, you will not be entirely correct in your answer. So we'll analyze that as we go along. Now, with the rearrangement and the data from experiment 2, we're going to plug in our numbers. You should correlate what's going on in experiment 2 with what we're plugging in here. Notice that molarity is squared here in the denominator and is also multiplied by molarity, so that's going to give us m cubed, molarity cubed. One of those, however, will cancel out, courtesy of the molarity in the numerator. So we're going to end up with units of slash m squared dot s. Another way to write that is m to the negative 2, s to the negative 1. You could, if you wanted to prove to yourself that you get an almost identical number using any of the other experiments, namely 1 and 3, you could try it, and you should get, if not precisely the same number, something very close. Finally, we now have a fully developed rate law. This means we could use any concentrations and plug them in and find out what the rate will be. And that's exactly what we're going to do. In the problem, we're given a certain concentration for NO, a certain concentration for H2. We plug them in, and we find that under these particular conditions, we will have a rate of 2.2 times 10 to the negative 4 molarity per second. That should always be our rate. Units, unless of course we're using minutes, but typically it's molarity per second. Honestly, it could be millimolar per second. It could be different things, but in general, it's a concentration unit over a time unit. You can imagine, I hope, how developing a rate law could be quite useful for chemists, because it gives chemists a chance to optimize reactions by understanding more precisely what the effects of varying concentrations of different reactants will be. This can be used alongside things like manipulations to temperature, to pressure, equilibrium considerations. It's a whole thing to bring all of these moving parts together to find out what will make your reaction the most efficient, but it's a very powerful tool for chemists in industry and elsewhere to manipulate reactions so that we get the best results possible.